Good afternoon. This is Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. So today we will discuss matrix approach to econometric modeling. In the last couple of lectures, we have discussed the fundamental issues of econometric modeling, and we have discussed econometric modeling with respect to bivariate systems, trivariate system, and multivariate systems. And we have also discussed various problems and assumptions which we have and which we like to use in the case of bivariate system, trivariate system, and multivariate systems. So up to till now we have discussed the fundamental issues of econometric modeling, which is one part of the one part of the econometric modeling. So in the next part of the econometric modeling, we have to discuss various issues and problems with respect to the econometric modeling, whether the problem is in a bivariate setup or in a trivariate setup or in a multivariate setups. So the moment or the once you have the estimated econometric modeling, then or you can say once we have the estimated econometric models, then obviously next step is to check for best fitted models, whether the estimated model will be considered as the best model or not. So the way we will check the existing estimated model to be the best, then there are certain steps and there are certain formalities we have to maintain, or we have to go through all these formalities. So this requires enough knowledge, enough structures, various techniques through which we have to make a judgment that the existing econometric model will be the best and it can be used for forecasting and policy use. So before we proceed to the second part of the models, econometric modeling, where we have to discuss various issues. So we like to highlight the same issue which we have discussed earlier, that to bivariate approach, trivariate approach, and multivariate approach. So here our idea is to apply matrix and to simplify the existing system which we have discussed earlier. So that means whether the problem is a bivariate setup or trivariate setup or multivariate setup, we can start with matrix and also you can solve with matrix. So up to till now we have discussed basic steps, then in between we use matrix little bit, so that the problem will be very simple one, and we through that simplicity we will get the estimated models. So today we will discuss very beginning of this econometric systems, and we will have the estimated models. By the entire first to last we have to see how matrix can help, so that you can say we will get the estimated models without less effort, or you can say without any complexity. So let me start or let me highlight how is this particular setup through which we have to proceed. So we have discussed in the last class, or couple of lectures back, so that y equal to beta 0 equal to y equal to beta 0 plus summation beta j x j x j i plus uj. So this is the initial setups I equal to 1 to n. Okay, so this is how the model is all about. We can set here, let's say yj here. So now the basic formality here is that, so we will assume that y structure is like this: y1, y2 up to yn, and x1 consists of that means this will be x1, x2 like this. So x1 is equal to x11, x21, x22 up to x2n. Okay, then sorry, this is x31 up to x n1, x21, 31, then n1. Okay, so similarly x2 equal to x21, x22 and x23 then it will go to x2n. So okay, and then similarly x3 is equal to x31, x32, then x11, x21, x31, xn1. So then it should be x13. Okay, it should be x31, x32, x33. Okay, x33 up to x3n. So this is how you have to proceed. Okay, so now similarly we have to find out xn, xn1, xn2 up to xn. Okay, so this is how the entire structure is all about. So by the way, we have to transport the entire system into matrix format. So how we will do that? So let us start with a simple models here. So like yi equal to beta 0 plus beta 1 x1I plus beta 2 x2I plus beta k xki, okay, plus ui. This is the multivariate, you can say, model with the k number of variables and I is sample observation. So here I equal to 1 to up to n, that is sample observations, and k is the number of, you can say, variables in the systems, that two independent variables. Okay, so because y is already 1. Okay, so how will we write this particular structures? If this is actually this is in implicit format, so we will try to put it in explicit format, so that the all the equations can be, you can say, it can be very structured and it can be easily understood. Let's see here. So y1 equal to beta 0 plus beta 1 x11 plus beta 2 x12 plus beta n x1n, okay, plus u1. So this is first equation, so let it be, call it 1. Then y2 equal to beta 0 plus beta 1 x21 plus beta 2 x22 plus beta n x2n plus u2. Okay, similarly y3 equal to beta 0 plus beta 1 x31 then plus beta 2 x32, okay, x32 then plus beta n x3n plus u3. Okay, this will call it 2, this will call it 3. Okay, it will continue like this. Okay, so then finally we will get yk, because k number of variables are there. Yk equal to beta 0 plus beta 1 xk1 plus beta 2 xk2 plus beta n xkn plus un, okay, plus uk. Okay, uk, because it is in kth series. So this is how the structure is all about. Let us assume that this is the step 1 of this matrix approach and this is step 2 of this metric approach. Okay, okay. Should I start once? Okay. So the step 1 process is to highlight the multivariate setup. So where yi equal to beta 0, beta 1 x1I, beta 2 x2I, beta k xki ui, where I represents number of sample observation in the systems and k represents number of independent variables in the systems and y is the dependent variable. So this is how the basic framework of multivariate models. So once you will expand that particular models, then we have series of equations like y1 equal to beta 0, beta 1 x11 plus beta 2 x12, beta up to beta n x1n plus u1. So similarly y2 equal to beta 0, beta 1 x21, beta 2 x22 up to beta n x2n u2. So it will continue. So in the kth series we will get yk equal to beta 0, beta 1 xk1, so up to beta n xkn plus uk. Okay, so this is how the entire system all about. So what you have to do, we will transport this particular system into a matrix approach. Okay. So now I will write simply here. I will write it here simply like y equal to x beta plus u. So the entire systems whatever we have discussed in the step 2, so I can represent or I can immediately transfer into this particular format. So that means instead of writing so many equations, so many variables and so many parameters at a time, so it's better you put in one equations and in a compact format, so that in a very small space and very small way you can represent the entire issues. Okay. So let's say here's y equal to x beta plus u. So how we have to represent, where y equal to the column vectors, so y1 y2 up to yk. Okay. So this is how the you can say y series all about. That means this particular format here, so y equal to x beta plus u is nothing but in a vector format. Okay. So that means here we are writing y and here we are writing x beta and u. So that means y has a series of component, x has a series of components, beta has a series of component and u has a series of component. Let us first put it in a particular structures, then we will expand it, how we will go for these estimations. So now the moment we will transfer the entire step 2 equation into step 3, where y equal to x beta plus u. So here y represents y1 y2 yk. So this is one matrix. Okay. So y is the variable which consists of y1 y2 up to you can say yk. Okay. So that means it is the order of k into or k cross 1. Okay. So similarly x represents here 1 1 1 up to 1. Okay. So this is 1, then x11 x21 x22, then it will come to xk2. Okay. So similarly x12 x22, then it will continue xk2. So x21 x, this is in fact the x31, then this is equal to k1. Okay. So that is the right structure. So then it will continue, then finally x1n x2n, then we will have xkn. So this is order of k into n. Okay. So that means k number of variables into k number of variables in with n observations. Okay. So that means the matrix x means it is the matrix of order k cross n. So k number of rows and n number of columns. Okay. So that means we have to represent again beta. So beta is equal to here, so like beta 0, beta 1 up to beta n. Okay. So this is one particular format. So then finally u. So u represents y1 y2, then uk, sorry, u1 u2 up to uk. So for beta the order is n cross 1, so n number of rows into 1 column. So this is also k cross 1, so it is k number of rows into 1 column. So now in the left side, so the moment I will write y equal to x beta plus u, so then obviously y is here, y here k cross 1. Okay. So that means the entire structure x beta plus u should be k into or k cross 1. So that means here x represents k into n. Okay. So then beta represents n cross 1. Okay. So then plus u represents k cross 1. Okay. So if you will target, then by matrix structures, this becomes automatically k cross 1. So that means x is a vector, beta is a vector. So when x has a order, you can say k cross n, and b has a order n cross 1. So obviously in the first case right side and the second case left side should be equal, then obviously this will be cross automatically. So obviously the entire multiplication will be order k cross 1 only. So this is k plus 1 and this is k plus 1. So this is systematic means efficient one. The reason is that you have to here apply this addition properties, because this is order same, this is order same, so addition can be possible. Oh, sorry. Okay. Okay. So now we have, so I will write it here once again. So y equal to x beta plus u. Okay. So this we will put it in equation number. So that means when we will go for matrix approach, then our starting process is from y equal to x beta plus u. Okay, because whatever we have discussed before that, then these are all basic information to come to that particular equation y equal to x plus beta. Until unless you have complete information about the setup, then you cannot understand this particular equation. So y equal to x beta plus u means it is derived from this particular setup. So where the system is a k number of variables, the two independent variables and one dependent variables y, and the number of observations are, you can say, n number of observations are there. So n number of observations, k number of independent variables and one dependent variable, that is y. So that means with one dependent variables and with k number of independent variables and sample size n, so we have to build a model, estimated model, through the application of matrix. That is the agenda which we discussed today. Okay. So now y equal to x beta plus u is the starting point of this matrix approach. So what I have to do, let us assume that my estimated model will be y head equal to x beta heads plus u. Okay, x beta head plus u. So now what I have to do here, x beta plus u. So by the way, how do I get a error component? So next step is we have to get the error component, e equal to y minus y head. Okay, so this is the error component. So now as per our earlier discussion with respect to bivariate, trivariate and multivariate, the moment we will get e, or that is error component, then obviously what we have to do, we usually make it sum squares, then we have to minimize with respect to corresponding parameters. If it is bivariate, then we have to minimize with respect to beta 0 and beta 1, because in the bivariate there are two parameters, and in the case of trivariate we have three parameters, beta 0, beta 1, beta 2. Obviously we have to minimize the error sum square with respect to beta 0 head, beta 1 head and beta 2. So similarly, if we add one after another, then obviously the equation will start adding. Okay, so obviously the complexity will start increasing. So now we will start with some different way. That means we have to assume that the entire structure is we are handling the entire structure at a time. Okay, so e equal to y minus y head. So that times we are making square and taking the summations. So here there is no concept of taking making squares and taking the summation. Here we have to apply matrix multiplication, the two application of transpose. Okay, so now e equal to y minus y head. So that means what is this? So it is equal to y minus, what is y head? So y head equal to, so this is y equal to x beta plus u. So y head equal to simply x beta. There is no question of u. Error component will be automatically removed. So that means y head equal to x beta head only. So this is equation number 2. So that means when we subtract y minus y head, we will get error component. So this is just subtractions. Okay, so original equation with this particular estimated equation. So that means it is nothing but y minus x beta heads. So this is y minus x beta heads. So I will write it here. So e equal to y minus x beta heads. All right. So now what is E transpose? E transpose we will call it y minus x beta head into its transpose. Okay, so before handling this particular problem, you must have a sufficient information or sufficient knowledge about this matrix. Matrix is simply, there are means there are many ways you have to represent the matrix. The simplest definition of matrix is to arrangement of elements in row wise and column wise, but that is not the case here. So we are not arranging here elements row wise and column wise. In the meantime, we are making systematic approach. That is that means here we are applying the application part of matrix. So how this matrix can be utilized properly to make the complex problem into simplex. So that is the basic agenda here. Okay, so this is how we have calculated E equal to y minus x beta and E transpose equal to y minus x beta head to the power transpose. Okay, so now so the moment you will get these ones, then we like to get summation E square. So summation E square, so that is error sum square is equal to E transpose E only. So E transpose E only. So this is how the you can say summation E square. So that means what is E transpose E? So let's say E equal to E1 E2 up to En. So E transpose E means, so the structure will be like this. So E1 E2 up to En. Okay, this is one column. So then another column is E1 E2 up to En. Okay, so that means the multiplication will be like this: E11 E22 then En. Okay, the cross product will be automatically 0 because this is our standard assumptions. Okay, so as a result we will get E transpose E. Okay, so E transpose E is nothing but y minus x beta head to the power transpose into y minus x beta head. So this is our entire structures. Okay, so this summation E square means y minus x beta head into y minus x beta. So that means summation E square is equal to y bar y transpose minus x beta head to the power transpose into y minus x beta heads. Okay, so this is how the entire structure is all about. So now we have to you can say we have to diversify it. So what you have to do? So summation E square equal to y transpose minus beta head transpose x transpose into y minus x beta heads. Okay, so this is how, because this is the as per the property of transpose, x beta head transpose means beta head transpose x transpose. Okay, so this is how the property all about. So I am not going to teach all these details about matrix, just if that you have to learn yourself. So here I have to give the only structure how matrix can be used to estimate this econometric model, that to multivariate analysis. So accordingly we have to proceed. So that means we are assuming that I am assuming that you must have some information about matrix. Until unless you have matrix complete, until unless you have complete information about matrix, it is very difficult to touch these ones, or you cannot handle this particular component. So obviously you have to first learn the basic of matrix, then you have to apply. For means if by any chance if you have no matrix knowledge, then you have to go by the simple structure of the econometric modeling, which we have discussed in the last class. Okay, so if you like to make it very attractive, and you like to save times, or you can say make it very beautiness, then obviously you have to learn matrix and you have to apply the matrix to get the system done. Okay, in a proper way or systematic way. So this is how the summation is square. So now what you have to do? So this is nothing but we have to go for multiplication. So y transpose y minus y transpose x beta head minus beta head transpose x transpose y minus plus beta head transpose x transpose x beta head. So this is how the entire multiplication all about. Okay, so now we will go for simplification. We have to simplify this one. So now this is nothing but y transpose y minus, I will write here 2 beta head transpose x transpose y plus beta head transpose x transpose x beta heads. So that means this particular component, this and this will be equal because it is a symmetric in nature. So that means y transpose x beta head is equal to beta head transpose x transpose y. Okay, and okay, so by if you apply this particular structures, then obviously the equation will be reduced to this much. So now beta head transpose is the our requirement, so we have to minimize with respect to beta head. Okay, so but remember here, beta head does not mean only one beta. Beta head indicates so many betas are there, so that means it is the set of beta 0, beta 1, beta 2 up to beta k. Okay, so there are series of betas are there, but we are putting beta. So here beta is not a individual component, rather it is a vectors. Okay, so d summation e square by d beta heads, so which is nothing but which is coming like this. Okay, so the structure will be like this, y so I can directly write here 2x transpose y, 2x transpose y plus 2x transpose x beta heads, because there is a property of matrix is that dx transpose ax by dx is equal to 2ax or 2x transpose a. Okay, so this is how by applying this particular component, and if you differentiate this particular structure, then obviously you will get this particular equation. So that means this should be equal to 0. Okay, so if you will make equal to 0, then obviously by simplification, if you will simplify, then x transpose y equal to x transpose x beta heads. Okay, so now x transpose y equal to x transpose x beta heads. So we need what is the value of beta head. Okay, so beta head, so that means what you have to do, we have to multiply x transpose x inverse in both the sides, because we need beta head. So if you will go to the right side, then obviously x transpose x is the extra component. So now if you will multiply x transpose x inverse, then obviously we can have only beta head in the right side. So because just like if A is a matrix, then by properties of inverse matrix, A inverse A equal to unit matrix. So obviously we will means we have to apply that particular properties of inverse matrix, then we have to find the solutions. So now if we multiply x transpose x inverse on the both the sides, then that will be like this: x transpose x inverse x transpose y equal to x transpose x inverse x transpose x beta. Okay, so now this and this is unit. So if I will take this is A, then this is A inverse, so that will be unit matrix. So that means this is called as unit matrix of order n, so beta. Okay, so that means it is equal to x transpose x inverse x transpose y. So that means what we will conclude here, so beta head equal to x transpose x inverse x transpose y. Okay, so this is the conclusions we have, or this is the result we have received from this particular analysis. So that means our structure is like this. Our structure is here, or starting point is y x beta plus u, then by the way we have y head equal to x beta head, then by the way we have e equal to y minus x beta head, and by the way we have e transpose equal to y minus x beta head to the power transpose. Then we have the multiplication e into e transpose. Then obviously we have to differentiate the sum squares with respect to beta, then we will get this equation. Okay, so now by this process we have received, by the simplicity we have received beta head equal to x transpose x inverse x transpose y. So that means what is x transpose x inverse? Let us see what is that. Okay, x transpose x inverse. So that means x transpose x inverse means we have to find out we have to apply the inverse matrix formula, then you have to do the job accordingly. So x transpose x is basically like this. So let's say x1 up to x2 up to, you can say, xn this side, and this side x1 x2 up to xn. Okay, so then we have to go for this into this, this into this, this into this, then this into this, this into this, and this into this, like this. Okay, so that means this particular item will be summation x1 square, this particular item is equal to summation x1 x2, this item equal to summation x1 xn, So similarly x2 into x1, okay, then summation x2 squares, then x2 xn, okay. So similarly xn x1 summation xn x2, then summation xn into xn, that is xn square. So that means x transpose x inverse means only this much, okay. So this is the x transpose x inverse matrix, okay. So similarly we get to know what is the x transpose y, okay. So x transpose y, that means we can write it here also, x transpose y. So that means we have to multiply the x transpose vectors, then y vectors. The product will give you x transpose y. So which is nothing but summation y, then summation x1y, then summation x2y, okay, x2y, then continue equal to summation xky, okay. So this is how the entire structures, all right. I'll write it once again here. So that means here x transpose x inverse means x transpose x inverse means this is summation x1 square, summation x1 x2, then summation x1 xn, okay, then summation x2 x1, summation x2 square, summation x2 xn, then continue, then summation xn x1, summation xn x2, then summation xn squares, okay. This is x transpose x inverse, and x transpose y is equal to summation y, summation x1y, then summation x2y, then summation xk y, okay. So this is how the entire systems, okay. So now, so why we are writing all these things? Because we have these structures, means by the way, when we have a x beta heads, then y head equal to x beta head, then beta head equal to x transpose x inverse x transpose y. So that means if you multiply this and this, then obviously you will get this particular product. This is nothing but this is n series n into k, and this is k into 1, okay. So you will get n into 1 matrix. So that means y1 y2 up to yn, that is the nth observations, okay. So now once you have the estimated, means if you go by as usual procedures, then first objective is to set the equation, then you transfer into mathematical form of the model, then sorry, that means you set the theory, then you transfer the theory into mathematical form of the model, then you have to transfer into the statistical form of the model, then you have to apply some technique to get the estimated model. The moment you will get the estimated model, then obviously next objective you have to go for checking the fitness of the model. So that means as usual we have two different structures, that to test the significance of the parameters and to test the overall fitness of the model. So now to check the significance of the parameters, so we have to means we need to calculate variance of all these parameters, then standard error of all the parameters, then followed by t statistics, and then you have to compare with the tabulated. Accordingly we have to look whether it is significant, and if it is significant, at what levels, okay. So whether it is 1% level or 5% level or 10% level, and whether it is through one tail test or two tail test. So this is how which we have already discussed all these details. So now in the time being in this particular matrix, so the moment you will transfer the entire complex problem into simplex by the by representing one simple equation like y equal to simply x beta plus u, and obviously by the way when we start estimating, then we have received y head equal to x beta head, where beta head equal to x transpose x inverse x transpose y, okay, x transpose x inverse into x transpose y. So we have already mentioned what is x transpose x inverse, and we have already known x transpose y. So now if we again multiply, then obviously the product will give you the coefficients of beta, that means the estimated coefficients of beta, that to beta 0, beta 1, beta 2 up to beta k, okay. So once you have this beta coefficient, estimated beta coefficients, that is from beta 0 to beta 1 beta k head, So next step is to check whether all these parameters are statistically significant. So that means we like to test whether beta 0 is significant or beta 1 is significant, beta 2 is significant, up to beta k is significant. So we have to set the null hypothesis accordingly corresponding to each particular parameter separately. Then you have to test one by one. Okay, so there may be possible because there are k number of variables. Some parameters may be significant, some parameters may not, and there may be possibility that no parameters will be significant, and there may be possibility that all the parameters will be significant. By it may be any case, that does not matter, but we have to check, we have to now justify what are the ways or what is the procedural measures how to check all these details. So now for that, the standard component we need is called as a variance of beta head, because here we are just getting the beta head coefficient, that is x transpose x inverse into x transpose y. So now when I write beta head equal to x transpose x inverse x transpose y, it looks like one component only, but beta is a vector here. So it involves beta 1, beta 0, beta 1, beta 2 up to beta k. So now since we are representing in a vector format, then as per the vector format, so we like to know whether this particular beta is statistically significant. So obviously if you like to know whether this particular beta is significant, then we like to know whether this this particular means we like to know what is the variance of beta head first, and obviously we like to know what is the standard error. Then we have to set the null hypothesis, then accordingly we have to calculate the t statistic and can compare with the tabulated statistic with a particular level of significance. So as usual you have to proceed accordingly. So in the meantime we need to know what is the variance of beta head. So here, so here beta head equal to x transpose x inverse x transpose y. This is how beta head. So now we need variance of beta head. Okay, variance of beta head is equal to here sigma square x transpose x inverse. Okay, so there is a mathematical derivation here. So how do we get this variance of beta head from the given beta head? So that is x transpose x inverse into x transpose y. So I am not deriving all these details because we have lack of time. So what that is the reason I am omitting lots of steps here. So what you have to know, so we just fit the entire system into the matrix approach. That means you put a single equation which can describe the entire structures. So then by the application of matrix, then we come to a conclusion. So that means we have the estimated beta coefficient, and we like to now check whether this particular beta coefficient is significant or not. So for that we need to have variance of beta head, and variance of beta head is calculated by this particular formula sigma square u x transpose x inverse. So now what is sigma square u? So sigma square u we have discussed. The entire structure is almost all same, just we have to put it is matrix approach is just like old wine in a new bottle. So we are just putting something in a very systematic way and more attractive way. That is all about this particular lectures. Otherwise these are the components which we have already discussed. Okay, so we are just representing in same different means in the different format. Okay, so now variance of beta head equal to sigma square x transpose x inverse. Okay, so what is sigma square? Sigma square equal to summation e square by n minus k. Okay, so n represents number of sample observation, k represents number of involvement of variables, that is independent variables. Okay, so now what is summation e square? Summation e square equal to summation y square minus y head square. Am I right? Summation y e square equal to summation y square minus summation y head square. Okay, so this is how we have to write. So now we know there is a concept called as a total sum square is equal to explained sum square plus residual sum squares. Okay, so this is nothing. Total sum square means this is summation y square, this is summation y head square, and this is summation e square. This is residual sum squares. So now how do we get all these details? Because this is all about matrix approach. Okay, so it is not as usual standard structure. So it may be similar line, but there is a little bit different. So we don't like to dig all these details right now. So we like to know what is the simple formula through which the job can be done. So that is our objective here. So now, so here sigma square equal to summation e square by n minus k. So summation e square equal to summation y hat square minus summation, so the summation y square minus summation y square minus summation y hat square. Okay, so now here, so we can write total sum square equal to summation y square. So it can be also, you can say, other way we can write it here. So that is nothing but y transpose y minus n y bar square, okay. So this is, that means what we are doing is summation e square y square means, so the way we have received summation e square, that means e transpose e. So similarly we have to get the summation y squares by multiplying y with y transpose. Okay, so the moment you will go for multiplication y transpose to y, then you will get summation e squares. Okay, so now if you simplify again, then the entire structure will be y transpose y minus ny bar squares. Okay, so this is TSS. Similarly, RSS equal to y transpose y minus beta hat transpose x transpose y. Okay, so then similarly ESS equal to beta hat transpose x transpose y minus ny bar squares. Okay, so this is TSS, this is RSS, this is ESS. Okay, so now we can check it whether TSS equal to RSS plus ESS. So now you see here, so if we club all these details, then obviously this and this will be cancelled. So obviously we have this particular structure only. So this is nothing but this ones. Okay, so that means summation y square equal to y hat y transpose y minus ny bar squares. Okay, so now our job is almost all done, because we need only what is the estimated beta coefficient, its variance. So once you get the variance, then obviously we set the null hypothesis, then you can get the standard error of beta hat. Means once you have a variance of beta, you make it square root, you will get the standard error of all these coefficients, means that to beta hat is. Then you have to set the null hypothesis. Accordingly, we will calculate the t statistic by beta divided by standard error of beta hat. Then ultimately we have to go accordingly. So that means we have to check with its tabulated statistic and also significance level. So that means, so this is one part of the story, in that to specification test, and that to significance of the parameters. The next part of the problem is to know this overall fitness of the model. So far as the overall fitness of the model, so as usual we have to we like to know what is the value of r square and r bar squares, that is adjusted r squares. Okay, so what is r square here? R square, as usual, means the formula is the ratio between exponent sum square by total sum square. So similarly we can also apply here, because r square equal to ESS by TSS, but here ESS is equal to beta hat transpose x transpose y minus n y bar square divided by TSS, that is y transpose y minus n y bar squares. So this is how the r square value is all about. Okay, so the moment you will get r square value, then accordingly we can get the adjusted r square. Adjusted r square is nothing but 1 minus r square into n minus 1 by n minus k. So this is not a problem. So once you have r square, then you can easily get r bar square, provided you must have knowledge on n and you must have knowledge on k. But here we are almost all in that particular structure. That means there are n observation and k number of variables. So that's why there is no problem here to means there is no confusion at all. So when we will handle a particular practical problem, that times n must be in a particular figures, exact figures, k also particular figure, that two exact figure. So accordingly you have to go for it, the adjusted r square. So similarly, the way we are testing the significance of the parameters through t statistics, here also we have to test the overall fitness of the model with the f statistics. So now as usual we like to know what is the f statistic here. So f statistic, again the ratio between exponent sum square with the residual sum square. So accordingly you will get, you can say, the f statistics. So again you have to check the tabulated statistic with the corresponding degrees of freedom, that is n minus 1 to n minus k. So obviously accordingly you have to see whether the overall fitness of the model, that to R square is statistically significant or not. If it is so, then you have to proceed accordingly. So that means what we have discussed till now is that we just transport the entire structure into particular format, so complete in a matrix approach. So in the earlier versions of our modeling, that to bivariate and trivariate and multivariate, we just start deriving all these equations, then we apply summation, accordingly we will get the estimated all estimated equations. That means we have to apply the OLS techniques, then we have to differentiate with respect to this error sum square to that estimated parameters, and ultimately with respect to particular modeling systems, that to bivariate, trivariate and multivariate, we estimate the parameters, or you like to differentiate the sum square with respect to all these parameters. Then once you have a standard equation, we transfer the standard equation to some particular, either in matrix format, or you can say by Cramer rule principles, or you can directly solve this simultaneous equation if you are very comfortable. If the problem is bivariate or trivariate, it is very easy to solve very quickly without having the touch of matrix, even converse rules, etc., etc. But when the problem is more complicated, that means when the system will be more than 3, more than 4, or you can say 5, 6, 7 like this, in that times it's very difficult to handle manually. So either you go with the software technique, or you can say there are standard, so many softwares are there. So you just enter the data and give click, you will get the results. It is not easy, it is not difficult at all. But if you have no statistical software, or if you are not allowed to use statistical software, then you cannot handle these multivariate problems within a time frame, and that too particularly for exam point of view, or you can say class point of view. So in that context, to transfer this complexity to simplicity, so what you have to do, you apply the matrix approach, then automatically you can get these things easily. Okay, so it is not it's not such a serious issue. So it is very easy to tackle the particular problem. So that means what we can conclude, that matrix has a lots of application, lots of utility, and that to use in econometric modeling. And most particularly when there is a multivariate analysis, then the matrix has a typical it has lots of beautiness, so that we can transfer the entire things into a simplicity format. So this is how the entire structure all about. So now whatever we have discussed, the matrix approach of multivariate modeling, we can examine, or we can justify the same thing with respect to a particular problem. So it does not mean that the matrix approach will be always applicable to multivariate problems. So even if in the bivariate setup, you can also we can also you can say apply matrix approach directly. But matrix approach is it's a very simple technique. But when the system is very consistent, means very the structure is very small, then obviously that times the matrix approach looks like a complex. But when the problem is bigger and very complex, then that times the matrix approach will make the thing very simpler. So that's why you have to take a decision, and you have to proceed accordingly. But in the meantime, it's not possible to handle many variables, and that to application of matrix, because ultimately whether using the simple analysis or matrix analysis, ultimately you have to handle the entire means all these variables at a time. So now when you will apply the matrix approach, then that too multiple variables, at times your size of the matrix will be bigger. So when the size of the matrix will be bigger, that means with respect to its orders, then matrix multiplication will be also very not so much difficult, but it will take lots of time, and it will add little bit complexity. So to transfer all these structure into simple, so what you have to do, you have to look into very carefully, then apply accordingly. So my suggestion is that when the system is very simple, that we can say bivariate and trivariate, then you can you need not require to use matrix. You can go ahead with the simple calculation only, a simple estimation process. And when the problem will be more complicated, like means particularly in the multivariate cases, so that times you have to apply matrix approach. But if you apply, if you are very smart and you have a very smart knowledge on matrix, then even if you handle this particular bivariate system itself, okay, so you use matrix very beginning and to till end. But generally this particular technique is useful just to get the estimated models. So now once the estimated models you have, then the things will be in other way around. That means after estimation models, the next step is just to check whether this model is completely reliable or not. That means it is free from all these errors. So that is how we are doing for all diagnostic test and all these significance test, etc., etc. So now so this means after estimation, whatever these steps are available to get the best fitted model, this means in that case matrix may not be very useful, but to get the problem means at the starting point to get the estimated model. So within that process, matrix has a lots of applications. Means after that there can be use of matrix, but that usefulness is not so important, because having the estimated models, then lots of things can be done easily without having the application of matrix further. Okay, so but to get the estimated models, that too means this particular component, that matrix approach to multivariate, is specifically very useful or very handy for classroom only, or that to exam point of view. But when you are handling big problems, particularly in research oriented problems or research projects, so that times obviously there is no point to do all these things in the room. So you have to directly handle with the softwares. So that times matrix has no utility at all. But specifically matrix has a utility when you are in the class and you have to your job is how quickly you can evaluate this particular model without having the use of softwares only. So then in that case, even if without the use of, you can say, Excel sheet, so you have to, everything you have to do through, you can say, matrix. So that times it is very easy. But when you have the opportunity to handle Excel sheet and you can say statistical software, that times it is not required at all to apply matrix approach. That means what is my conclusion is that matrix approach is basically very useful when there is no access to internet, or you can say Excel sheet. If there is access to internet and Excel sheet, that times it is not required at all the use of matrix approach. So in the with this we can conclude this particular session, and in the next class we will discuss the same matrix approach to multivariate with a particular problem. So we are just theoretical discussing these issues, but practically how we have to design all these structure into in the matrix format, that is more interesting and more attractive. So that we will discuss in the next class. Thank you very much. Have a nice day.